beautiful people, and welcome. In today's video, we are continuing our discussion about trig identities, and we are going to be adding some trig identities to our bucket of knowledge. So let's start with how do we rewrite using identities? So the first thing you're going to do is you're going to check to see if you can rewrite everything in terms of sine and cosine. If you see a tangent of x or a cotangent of x, this could be squared. Think quotient identity. So tangent is sine over cosine, and cotangent is cosine over sine. Then you're going to see a trig function in the denominator. So if you see one, think reciprocal identities. For example, if you see secant in the denominator, think cosine. If you see cotangent, then it's 1 over tangent, right? If you see cotangent in the denominator, it's just tangent. And if you see a square, think Pythagorean identity. Try to rewrite first squares as like sine squared over cosine squared or cosine squared over sine squared. It can work better for you, but if it's a binomial, anything with 1, adding or subtracting, think Pythagorean identity. Doesn't have to be it, but it most likely will. Let's do some examples here. So I have sine of x times cotangent of x. So sine stays as sine. Cotangent is the tangent and cotangent identities or quotient identities. So it is cosine of x over sine of x. We're going to make sine of x into a fraction. Since we are multiplying, it is okay to divide diagonally. And we're left with just cosine of x as our simplified answer. Now let's say we have something like this in the denominator. We know that cosine has a relationship with secant. Now this is cosine squared, but because it's in the denominator, we do not need to use the Pythagorean identity. Save the Pythagorean identities for like the binomials where you're adding or subtracting 1. So since we have cosine in the denominator, it is the reciprocal of secant. And since cosine is squared, we're going to square our secant as well of x. Now, sometimes you're going to need to use some algebra. So if there are multiple fractions, you're going to need to bring them together. Adding fractions needs common denominators. If you're multiplying fractions, it doesn't require common denominators, and you could just multiply straight across, not diagonally, but straight across. Sometimes you're going to need to split a single fraction into 2 parts. We saw that in our last video where we had a binomial in the numerator, and we can split it into 2 fractions instead of 1. Sometimes you're going to need to factor out common terms. We saw that in the previous video as well. Sometimes you're going to need to distribute. And if it is a complex fraction, so a fraction over a fraction, you're going to use the KFC method. You're going to multiply by the reciprocal of the denominator. Your keep, change, flip. Let's go and do an example. So here's an example of factoring out. I see a tangent here. I see a tangent here. It is a binomial, right? You have one chunk minus a secondary chunk. So I'm going to remove a tangent from both by factoring it out. Left over, I have a cosecant squared of x minus tangent removed is 1. Now, should be alert, alert, alert. I have a something squared with a 1 attached to it. It could be an identity. Let's see. Cosecant minus 1, there it is, cosecant minus 1 is equal to cotangent squared of theta. So we're going to rewrite this as cotangent squared of theta, or in this case, x. We are still multiplying that by tangent of x. Oops, tangent of x. And so we have 2 things. We have tangent, which is sine over cosine. And we have cotangent, which is cosine over cosine squared of x over sine squared of x. I'm going to rewrite that here. So tangent was sine of x over cosine of x times cotangent is the reciprocal of tangent, so that was cosine of x over sine of x. But notice that the cotangent we are working with is squared. So that means cosine and sine both have to be squared as well. Rewrite that one more time. Sine of x and cosine of x, that's fine, nothing wrong with that. Cosine squared of x is the same thing as saying cosine of x times cosine of x. They just combined it. Same thing with sine of x times sine of x. Now I am rewriting this to help you guys see that you can divide sine and you can divide cosine. You're still left with cosine of x over sine of x, which is still cosecant, but this time it is singular and not squared. So cosecant of x is your simplified answer. Next one we have is secant of x over tangent of x. Secant is the reciprocal of cosine, so 1 over cosine of x. Tangent is sine over cosine. We have a keep, change, flip moment. We're going to keep, we're going to change, we're going to flip. So we have keep 1 over cosine of x. We're going to change this and flip this cosine of x over sine of x. We're going to divide cosine by cosine, leaving us with 1 over sine of x. Since sine is in the denominator, that means we have a reciprocal function. Sine has a relationship with cosecant, so that means cosecant of x is our reciprocal function. All right. Okay, so new ones. Introducing to you for the very first time are cofunction identities. Now, cofunction identities, they look scary, but I promise you they're not. They are just translations of the same graph shape. So in our discussion, when we were talking about sine and cosine, we said that sine wave, when graphing, blends into a cosine wave when graphing. So if we just shift it by some sort of angle measure like theta, your sine wave becomes your cosine wave, and your cosine wave becomes your sine wave. Tangent and cotangent have that same relationship with graphing. Secant and cosecant have that same relationship with graphing. You just shift it over. This is your h value. This is your horizontal or your phase shift. You just shift it a specific value, and it becomes an overlapping with each other. Those are your cofunction identities. How to use them is you're going to use the cofunction identities to replace with cosine. So if you, for example, see cosine of pi halves minus theta, you will remove it and replace it with sine of theta. We'll see examples like that. And introducing you for the very first time are odd and even identities. Now we've seen odd and even functions in semester 1 in my class. This time we are applying odd and even to trig functions. Now for cosine and for secant, they will have the negative. If the angle is negative, the negative disappears. For everything else, sine, cosecant, tangent, cotangent, you're actually bringing the negative out front. Okay, how do we use this? Let's do some examples. Let's say we have cotangent, and I'm going to keep this handy, so don't put that away too far. So cotangent of x is cosine over sine. Now you can use the other identity, the reciprocal identity here. Might probably be easier. I might show you that. Times tangent of negative x. Now if we look at the odd even, tangent, tangent is an odd function, meaning the negative comes out in front. So we are now multiplying by a negative tangent of x. Still multiplication, but now we're multiplying by negative. Now, tangent is sine over cosine. Again, you didn't have to take this route. You could have used the reciprocal identities. I'm just using these identities. Sine over cosine, keeping that negative. Sine divides with sine, cosine divides with sine. We're left with just that -1. If you wanted to do, it's bothering me, so I'm going to do it. If you wanted to redo this question using the reciprocal, you're still going to have to evaluate that tangent. Tangent still becomes negative tangent of x. We have that cotangent. And so how to use the reciprocal is we know that cotangent and tangent are reciprocal functions. So I'm going to rewrite this as tangent 1 over tangent of x times negative tangent of x over 1. And like before, tangents cancel. They divide out, and you're left with -1 as your answer. Okay, so here is the cofunction example. We have cosine, so we're going to bring cosine down. Nothing to do there. And then we see this weird looking thing. We see secant of pi halves minus theta. So we go into our little bucket of knowledge. Secant of pi halves minus theta is equal to cosecant of theta. So that means that all of this becomes cosecant of theta. Then we can continue solving just regular. We have cosine of theta times cosecant is the reciprocal function of sine. Multiply, here's my 1. So we have, oops, cosine, can I save it? Yes, I can. Cosine of theta over sine of theta. Cosine over sine is the reciprocal function of tangent, which is cotangent of theta. Next one, similarly, we have secant. Secant is the reciprocal function of cosine. Sine of pi halves minus x. Now they did not use theta here, they used x, which is okay, not the end of the world. It's the same thing. So we're looking at sine of pi halves minus x, sine of pi halves minus x. They used x instead of theta, which is cosine, and we're going to use cosine of x here. Put a 1 underneath it, and you notice that they cosines divide, so we're just left with 1 here. I believe we have 2 more examples. Let me take a, yeah, we have 2 more examples. This one, when I originally looked at it, did give me a little bit of a hard time, just because it's easy to make a small little hiccup, and I'll point that out. Okay, we have a lot of things. We have odd and even, and we have cofunction identities combined. Break them apart. Here we have a cofunction identity. Cosecant of pi halves minus x, cosecant of pi halves minus x is equal to secant. Next, we have a negative cosine of x. So I'm going to bring this negative first. Then I'm going to evaluate the cosine of negative x. Now, cosine is the only one, and secant, so one of two, that ends up absorbing that negative. The negative does not come out. So this becomes cosine of just x. This negative is this negative. Okay? The negative inside disappeared. Next, we bring down this negative, and we're going to evaluate sine of negative x. Now, sine is the one of many, right? One of 4 that brings the negative out. It doesn't absorb it, it brings it out. So we have negative sine of x. Now here's where the hiccup can happen. Be careful, because this is saying times tangent of negative x, tangent of negative theta, brings it out. So we have negative tangent of x. This is not subtraction. This is multiplying by negative. Big deal. This is subtraction. So here, yes, you can change this into addition because originally it was subtraction. Here, we cannot make it into subtraction because we have multiplication. Be careful. Let's write this out. We have secant, which is 1 over cosine of x minus cosine of x plus sine of x times a negative tangent, which is sine of x over cosine of x. I'm going to focus on here because this is multiplication. I'm going to put a 1 underneath it, and that gives us a negative sine squared of x over cosine of x. Sine times sine is sine squared. 1 times cosine is cosine. We have a negative. We have a negative. Here, I'm going to put a 1 underneath and focus on these two. I have 1 minus cosine, cosine, and 1, but we do not have common denominators. So that means I'm going to have to multiply by cosine of x, cosine of x. So that means I have 1 minus cosine squared of x all over cosine of x. We still have that addition. Technically, it's subtracting here, but I'm going to bring that addition down. Alert, alert. Is this a Pythagorean identity? Maybe. So let's take a look at our cheat sheet. We're looking for 1 minus cosine of x. 1 minus cosine of x squared, right? Cosine squared of x to be exact. It has to be squared to be the Pythagorean identity, is sine squared of x. So we can change that into sine squared of x over cosine of x plus a negative sine squared of x over cosine of x. Now, because we already have common denominators, we don't need to create them. We can just combine sine squared of x minus sine squared of x over cosine of x. Sine of x minus sine squared of x, this is just 0. And anything 0 divided by anything is just 0. So 0 is your answer. Last example, promise. Okay, we're going to take a look at a 30, 60, 90 degree triangle. You're going to use cofunction identities to show that cosine of 60 is equal to sine of 90 minus 60. Now, it is a little bit trippy looking because of the degrees. Like, we haven't been using degrees, we've been using x's and thetas, but all of this is corresponding to the graphing and then to the unit circle and then to the special right triangles. So let's focus here on this side. You're verifying an identity, which you're going to choose one side to work with. I'm going to choose this one because it looks like there's more to do here. We'll see. Okay, sine of 90 minus 60. Well, sine of 90 minus 60 is just 30 degrees. We're literally subtracting the degrees. Then we're looking at the 30, 60, 90 triangle. And you can also think about the unit circle if you need help remembering your stuff. So here is 1/2. Here is root 3 over 2. And if you're thinking about 30 degrees, here's 30 degrees. And our points are root 3 over 2 and 1/2. I'm writing that pretty small on purpose. And then we have our 60 degrees, and we have our points of 1/2, comma, root 3 over 2. Sine, here's cosine, comma, sine. That means cosine is our x, sine is our y. So cosine, sine, so sine of 30 degrees is 1/2. And then let's deal with cosine of 60 degrees. Cosine of 60 degrees is also 1/2. So because they are equal, we have proved that 60 degrees, cosine of 60 degrees, is the same thing as saying sine of 90 minus 60. All right, beautiful people, I promise this was the last example, and it is. Enjoy the rest of your day, and I will see you in the next one. Bye.